at least we see your slides and we hear you.
Perfect. Okay, perfect. Okay, thank you a lot. Mario, as you mentioned, you can see me?
Yeah, we can see you.
Okay. As you mentioned, my talk and the work is a joint work with Claudia Landi and Anife Varli, and the main topic of this talk will be Morse theory and its discretization. So, as you probably most of you already know, Morse theory is a powerful topological tool for efficiently analyzing a manifold, not directly, but studying the behavior of a smooth scalar function defined on the manifold itself. It has several effective applications in data segmentation, homology computation, multi-resolution analysis, and so on. And several discretized versions has been proposed in the literature. Among those, two discretized versions of Morse theory has gained a prominent role in the literature and the implication. Properly, piecewise-linear Morse theory, PL Morse theory by Botsch, and discrete Morse theory by Foreman. Being two discretization of the same smooth theory, obviously the two theories have several points in common, but at the same time they have quite a lot of difference. PL Morse theory is specifically defined for manifold domains, while discrete Morse theory does not have this constraint, and it deals with arbitrarily discretized domain. On one hand, PL Morse theory explicitly needs a scalar function defined on the vertices of the domain in order to construct critical points and the entire machinery of PL Morse theory, while discrete Morse theory does not explicitly need a function, but it adopts a more gradient-based approach in order to be defined. One of the crucial difference between the two theories is concern the notion of critical elements. For PL Morse theory, critical points are actually vertices of our discretized domain, while in discrete Morse theory, critical elements are simplexes in general of any dimension. And this difference creates a huge gap between the two theories. PL Morse theory is in some sense closer to our intuition, and as you can see in the image on the top of the slides, the highlighted critical points somehow are close to our intuition of a minimum, maximum, and saddle point, while the combinatorial approach provided by discrete Morse theory and the fact that critical elements are not vertices but simplexes could create a little bit of confusion and create a gap between the two theories, because as you can see on the right, the critical simplexes does not appear in correspondence with the critical points that we have on the left. For instance, if we consider maximum points on the left depicted in red, we have a single maximum on the left image, while we have two different maximum simplexes depicted by the two red triangles on the right. Is it possible to establish a correspondence between these two notions of critical elements and create a one-to-one correspondence between these sets, and so creating a bridge between the two theories? In this talk, we would like to answer to this question, and will be the outline of our talk. First of all, we will draw some background notion in piecewise-linear Morse theory and in discrete Morse theory, focusing on the definition of critical elements. In particular, for the PL case, we will see that there are several notion of critical points, and we will prove the equivalence among all these notions given in literature. Then we will be ready to establish, to claim the correspondence between these two sets of critical elements, and this correspondence will be realized under the hypothesis of having a relative perfect discrete gradient vector field. And as a last contribution, we will see how these RP gradient vector fields can be computed by an algorithmical strategies that we will introduce, at least up for simplicial complexes up to dimension 3. And in the end, we will draw some conclusion and we will address some future developments. So let's start with the definition given in PL Morse theory for the notion of critical points. First of all, let's put ourselves in the following framework. We have a combinatorial D manifold. In this case, D would be equal to 2, and we have an injective scalar function defined on the vertices of this combinatorial manifold. Benchov, in his work, characterized critical points, critical vertices of this manifold in terms by counting the number of triangles having the middle for the function f. In the example that you see on the right, if we consider vertex 5 has those highlighted 4 triangles, middle for in which 5 is middle for f, and based on this number we can by adopting the below formula we can realize that 5 is a saddle point for this piece of combinatorial manifold. Another definition, again for the case D equal 2, has been given by Brunner in 2001, and in this case the criticality of a vertex is characterized in terms of the number of wedges of its lower star, where wedges are nothing but a sort of slices in which is decomposed the lower star of the vertex, and the lower star of the considered vertex is simply the collection of simplexes of our simplicial complex having as a maximum value among its vertices for the function the value lower or equal than the value assumed by f of v. So in this specific case, we have 2 wedges, and according to the depicted classification, again, 5 is likely, again, a saddle point for our combinatorial manifold. In general, Bremen-Kuhnel define a different characterization for critical points in the framework of combinatorial manifold of arbitrary dimension, and they actually characterize the criticality of a vertex in terms of the relative homology of a sublevel set with respect to the same sublevel set minus the considered vertex. And again, according to this classification, 5 is classified as a saddle point for our function. One last definition has been given by Brunner and Arer, and again, this is a definition for an arbitrary dimension combinatorial manifold, and it characterized the criticality of a vertex in terms of the reduced homology of the lower link of the vertex itself. So we have a bunch of different notion for PL critical points for piecewise Morse theory. But what we have proved, luckily, is that all these definitions are equivalent. So if V is critical, is a critical point of a certain index and a certain multiplicity for a certain definition, then it is a critical point with the same index and the same multiplicity also for any other definition previously introduced. So all the PL notion of critical points are equivalent. Let's move to discrete Morse theory. As we mentioned, discrete Morse theory does not need explicitly a function for being defined, but it's based on the construction of a discrete gradient vector field, V, which is simply a collection of pairs of simplexes of our simplicial complex. Pairs are depicted as arrows in our surface in our example, and a collection of pairs that cannot create closed path in order to be addressed as gradients. In this framework, critical points and critical simplexes actually, because discrete Morse theory, in discrete Morse theory, critical elements are critical simplexes rather than simplex and simply vertices, are those simplexes not belonging to any pair of the gradients. So we have a notion, we have proven the equivalence of all the notion of PL critical points in the PL framework. We have a notion of a discrete critical simplex in the framework of discrete Morse theory. We want to connect those two notions and create a correspondence. And first of all, to do that, we put ourselves in a common framework, so in a framework where we have a simplicial complex, which is a combinatorial manifold of arbitrary dimension, endowed with a scalar function f, and on which is defined a gradient vector field V. The correspondence that we want to establish will be realized under the assumption of that V is a relative perfect gradient with respect to the function f. And this relative perfectness condition is defined as, is realized when the number of these critical I-simplexes for a certain function value coincide with the number of variation in the high homology group occurred at the same function value. So number of critical I-simplexes correspond with the number of variation in the high homology group. So just to depict an example, on the left we will see an example of a relative perfect gradient, since we have a variation in one-dimensional homology, and we have one critical simplex depicted in red of dimension 1, so the two numbers coincide, while on the right picture we don't have the same correspondence, and so the gradient is not relative perfect. So based on this notion, we can claim the correspondence between critical sets, PL critical points, and discrete critical simplexes under the assumption that the gradient is relative perfect with respect to the function. We have that vertex V is a PL critical point of index I and multiplicity Ki, if and only if there are exactly Ki discrete critical I-simplexes of V for which V, the vertex V is one of their vertices and they have the same function value. Rephrasing this theorem, we have the corollary, establish a 1 to Ki correspondence between PL critical points and discrete critical simplexes. And under the assumption that F is PL Morse, so if F is free of critical points of multiplicity greater than 1, this correspondence is actually a bijection. An example just to visualize this correspondence, on the right we have a gradient which is relative perfect with respect to the function that you see on the defined on the vertices, and as you see there is a correspondence between critical simplexes depicted in blue, red, and green on the right, and PL critical points depicted with the same colors on the left. And not only we have a one-to-one correspondence between these two sets, but there is also a sort of geometrical correspondence between these sets, because, for instance, the red triangle corresponding to the red point on the left actually have the red point among its vertices. And so it's the triangle is not only in correspondence with the red point, but is geometrically close to the red point 6. So we have seen that under the assumption that we have a gradient vector field which is relative perfect, this correspondence is realized. And one can ask, yes, but how easy is to realize this hypothesis? And we propose in our paper a strategy in order to build a relative perfect gradient vector field for simplicial complexes up to dimension 3. So up to this dimension, we will have a RP gradient vector field, and so we will be able to realize such a correspondence. These are the steps in order to build such a relatively perfect gradient vector field for complexes up to dimension 3, but I think I'm going out of time, so I prefer to focus on the conclusion and the future developments. So in the presented work, we have established a correspondence independent by the dimension between the set of PL critical points for the PL Morse theory and the discrete critical simplexes for the discrete Morse theory. This is one of the first results trying to answer to this question. The only other work dealing with this kind of question is a work by Leviner, in which an answer is given, but the solution is limited to dimension 2, and in order to realize such a correspondence, several barocentric subdivisions are needed. And moreover, we have shown a sort of algorithmical strategy for building a relative perfect gradient vector field, which will enable such correspondence. This correspondence is just a first step in the direction of creating a full bridge between discrete Morse theory and PL Morse theory in order to take advantage of the pros of both theory. And the next step in the future will involve the Morse-Mail complex, bifurcation theory, and extraction of steep and descent PL flows. And with this, I would like to conclude, and I wish to thank you for your attention.
Thank you very much. Are there questions by the audience?
I have a question. Great talk, Federico.
Sure.
Do you have any notions of correspondences for persistence? So we have level set persistence in the PL side.
Yes, in some sense, the relative perfectness defined here is nothing but a sort of perfection rewrite in terms of persistence. So relative perfect gradient is a gradient which respects the persistence induced by the sublevel sets of our combinatorial manifold induced by the function f. So the relative perfection actually asks that the number of variation in homology that correspond to the number of newly created and destroyed homological class at a certain step of a filtration, if you want, correspond to the number of critical simplexes of a specific dimension. In general, we don't have an equivalence between these two numbers, but when these two numbers coincides, we can speak about a relative perfect gradient, and the correspondence is realized. So yes, and as we know, in some sense, the definition of PL critical points given by Brehm-Kuhnel help us to realize that critical points, PL or discrete Morse critical points, since now we have a correspondence, are in correspondence with the change in homology of the filtration induced by the sublevel sets of the function f.
Thanks.
I don't know if I really answered to your question, but I'm glad.
No, that's good. Sure.
Any other question by the audience? Okay, if this is not the case, I don't have a question myself.
Okay.
Then thanks again for this nice presentation. And now I have one question to the organizers. So first of all, let me apologize to all of you for this super chaotic session. The first talk was okay. The last talk was okay, but Chiara's talk was completely messed up. So sorry to you. Now my question to the organizers, if you're listening, is can we give Chiara the chance to give the talk a second time? Because also the video recording will be totally messed up. So there's no chance that other people might see the video recording of the talk, maybe because they are in a different time zone and are sleeping right now. Would that be an option? Chiara, would you be interested in this? And to the organizers, would it be possible to organize this, that we put her talk a second time in a different session?
Yeah, we should definitely consider all the options that we have. So what we for sure can do is that we can add to the YouTube channel a recorded version of the talk. So we might ask her to record the talk and then make it available to everyone. I don't know if we have other open slots for talks, but I will discuss this with Frederick.
Okay. Good. That was an exciting session. We learned new features or non-features of Zoom. Thank you for your attendance and enjoy the other sessions in the conferences. Thanks.
Thank you a lot. Bye.
Thank you. Bye.